Good morning, my dear students. Myself Veerabhadrappa, Assistant Professor, Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Bangalore. Welcome to VTU e-learning for the subject Analog Electronics. The syllabus consisting of that 5 modules. Module 1, that analysis of AC analysis of transistor. Module 2, FET and its analysis. Third module is frequency analysis of FET as well as BJT. Fourth module is feedback, and fifth module is power electronics and regulators. To understanding this transistor modeling, it is necessary to understand a transistor diodes and introduction to the diodes and its transistors. In this introduction, we are going to discuss that diode characteristics, diode parameters, and transistor and its parameters. The objective of this course is a diode structures and its operation, and then we are going to determine the parameters of a diode, dynamic resistance, a capacitances, and next followed with a transistor operations, current and voltages, and characteristics and parameters. Diode structures, when that p-type and n-type semiconductors are combined together, that p-type semiconductor as a majority charge carriers holes and n-type semiconductors consisting of that majority charge carriers as an electrons. When these two combined together, then that charge carriers are moving from higher concentration to the lower concentration. During this process, the positively charged particles are bonded with a negatively charged particles, and it forms a negative ions, and a negatively charged particles combined with a p-type holes, it forms a positively charged electrons, it forms a depletion region. In the depletion region, which has the voltage potential barrier of that 0.7 for silicon and 0.3 for germanium. During this diffusion process, the diode formation, it followed through 4 steps. One is a diffusion, a diffusion process, and second process is a depletion region, third one is a drift and equilibrium state. During the diffusion process, these electrons it forms a potential barrier. When that potential barrier exists, then that some few more charge carriers are strongly negative electrons of negatively charged electrons and a strong positive electrons holes trying to diffuse through that channel, but that net current is 0, because at the same time, due to the minority charge carriers, that charge carriers are drifted from one region to the other region. That net current is 0, and then that at the equilibrium state, there is no current flowing through that PN junction when it is open circuited. The diode operation, the diode if you consider the PN junction, that p-type and n-type charge carriers, that a variation of that voltage from a negative voltage to the positive voltage as shown in that figure B, and then when that diode is open circuited. When the diode is open circuited, there is no current is to be flowing through the circuit, and then due to the potential barrier, that a delta V voltage as shown here, a difference voltage, that is a negatively charged particle to the positively charged holes. If you consider the VI characteristics of VI characteristics of the PN junction as shown in that figure. When that diode is forward biased, means that positively charged particle is connected with P-type material and negative terminal of a battery is connecting to the N-type material. Due to this, then where is the voltage V? If the voltage V is less than that V gamma, there is no current is to be flowing through that diode, because that applied voltage is not sufficient to cross over the depletion region or potential barrier. If that voltage exceeds, means if the voltage is varies linearly, if that voltage exceeds or greater than or equal to V gamma, then that current is linearly increasing, and then if the further increase in the voltage up across the diode remains constant, about 0.7 for silicon and 0.3 for germanium, and then current increases exponentially. If you can if you consider when the diode is reverse biased, that P-type material is P-type is connecting to the negative terminal of the battery and N-type is connecting to the positive terminal of a battery. Then if the voltage increases, then that initially that current flowing through the diode linearly due to the minority charge carriers, as the voltage applied voltage increases, that potential width barrier is increases or depletion width is increases, and then current flowing through the circuit remains constant. If the further voltage is applied, due to the Zener breakdown, that suddenly all the covalent bonds are broken and then suddenly current flowing through the circuit as shown here. When this voltage is to be in terms of milliamperes. This breakdown voltage is about more than 75 volts for a small diodes is up to the minus 200 volts. Now, when the diode is forward biased, that current is to be flowing through that, it is acting as a conductor, then its resistance is very small. When the diode is reverse biased, it is acting as an insulator, it is an open circuit and its resistance is very high. If we consider the diode parameters, when you from the study from this transfer characteristics or VI characteristics, the diode current you have to measure that a maximum forward current, a negative breakdown voltage minus BR, and then you are going to measure the diode resistance and a capacitances. The diode resistance can be measured in two ways. One is a static resistance and other one is a dynamic resistance. The static resistance is defined as you have to measure the resistance of a diode at a particular instant of time. For example, it is shown in this figure. At this point, the current flowing through this is to be about something IA. The voltage up across this diode is to be given by an VA. Then a static resistance of a diode, this is denoted with RD. It is given by RD and then it is given by a current VD by VA by IA. Means it is simply a ratio of that a voltage to the current. The dynamic resistance is also known as a incremental resistance and is also known as an AC resistance. It can be obtained by determined by taking the slope of the VI characteristics. You have to measure that change in the voltage and a change in a current. That change in the current, it is denoted with a symbol A, B, C. Then that dynamic resistance is denoted with a small r suffix D, that is given by delta V D by delta ID. And then this is to be equal to nothing but from BC by AB from the graph. If you want to measure the dynamic resistance, and then here we are to defining with respect to the forward current, and then it is denoted with RF, and if the reverse biased condition, that dynamic resistance is to be obtained by using this region. This change in this voltage with respect to current is denoted with RR, and it is to be given by delta VR by delta IR. This is a graphical analysis of this diode parameters. And if you measure the dynamic resistance and also it is analyzing that circuits, the diode can be analyzed by using a graphical method or a circuit analysis a graphical method. In the graphical method, this can be obtained by using, we know that if you consider the diode is followed with a resistance or a current limiting resistance, and then it is when this diode is forward biased, then that current is to be flowing through this diode and it is denoted with IF. That voltage this is to be V, apply VI, and then voltage drop across this diode is to be denoted with a VF. Then to determine the operating point of a transistor, we need to solve this diode circuit. If you are applying KVL to this input circuit, we are going to get VI is equal to minus VD minus IF into R equal to 0. If you are solving for this either VD, this is equal to a VI minus IF into R. There are two unknowns in this equation, means you have to determine the either value of the current flowing through the circuit or a voltage across the diode. Either you have to assume any one of the parameter, either IF and or VD, that every students get a different answers if their assumptions are different. Then if you have a characteristic curves, and then if you know the resistance, the value, this load line means you have to draw a load line between on the characteristic curves, where you have to determining this value, we have to setting that a voltage up across the diode is equal to 0. This maximum current flowing through the diode is given by a VI by R. When IF is equal to 0, you are identifying this point, and then the current flowing through the voltage drop across this diode is nothing but maximum, that is equal to VI. Then you have to connect these 2 points which intersects these transistor characteristics, diode characteristics. Then this point is nothing but the operating point or a Q point of a diode. This can be obtained also instead of a graphical analysis. We can also solve by solving this mathematical analysis. Next, to determining this diode parameters, and then these diode parameters RD, RR are used to measure or the modeling a diode. From the diode characteristics, we know that consider the okay. If you consider the diode a PN junction, that PN junction is offers the junction, this is a positively charged P type and an N type a semiconductor, and which is a positively charged holes are the majority charge carriers, negatively charged electrons are the minority charge carriers. It mentions a potential barrier, this is negatively charged particle ions and positively charged voltage. Due to this, a junction or a potential barrier width, this is to be denoted with width. Width W. When the junction is reverse biased, then the charge carriers are moving, majority charge carriers are moving away from the junction and minority charge carriers are moving across the junction. This current is known as a drift current. Due to the drift current and that width is increases, then this potential barrier junction is acting as a two plates of a parallel plate, then capacitor, then that capacitor C is given by epsilon A by W. As the applied voltage increases, that width is increases, then this capacitance is known as a stray capacitance or a transition capacitance, and it is denoted with CT. When the diode is forward biased, and then the charge carriers are diffused from a one junction to the P type to N type and materials, that holes are moving, and then due to the diffusion current that a capacitor is existing, then this capacitance is to be given by C is given by dQ by dV, where Q of a charge carrier is given by Q is equal to I into T, where I is the diode current and T is tau is the mean lifetime of a charge carrier, and then this can be obtained by a different, this C is nothing but a differentiating I d into T d by dV. When differentiating these equations, you are going to get on a capacitor C voltage, where that diode current is given by I naught into e to the power of V d by neta V t minus 1, where I d is the forward diode current, I naught is the reverse saturation current flowing through the circuit, and then V d is the voltage drop across the diode, and neta is a constant. Neta is equal to 1 for silicon and 2 for germanium, and V t is the voltage equivalent of a temperature, where V t is given by, that K T by Q, where K is the Boltzmann constant. This value is equal to 1.38 into 10 to the power of minus 23 joules per degree Kelvin, and T is the temperature in degree Kelvin, and Q is the charge of a electron or a hole, that is given by 1.6 into 10 to the power of minus 16 coulombs. Then at room temperature, that V t is approximately equal to 26 millivolts. As the temperature increases, then V t is also increases. If you differentiating this equation with respect to I d, then capacitor C is given by a tau into I d by neta V t. This implies that a diffusion capacitance C d is directly proportional to the diode current and inversely proportional to the temperature. And mathematically, that diode resistance is obtained. How do you determine a dynamic resistance? The dynamic resistance is to be determined by mathematically by differentiating that I d is equal to I naught into e to the power of V d by neta V t minus 1, where you are differentiating this equation with respect to V d, because we already defined that dynamic resistance R d is given by delta V d by delta I d. This can be obtained by graphically, and this dynamic resistance is also by differentiating this equation. This delta change in voltage to be defined as simply a small change in incremental, instead of an incremental, partial derivative of this diode voltage to the diode current. This can be also replaced with dVd by dId. Means you are differentiating that equation Id with respect to Vd, then that provides the dynamic resistance. Because this diode is a operating region, there are two regions, when the diode is forward biased and when the diode is reverse biased. When the diode is forward biased, the diode current is denoted with an IF, that is equal to approximately equal to I naught into e to the power of V d by neta V t, because that e to the power of V d by neta V t is much greater than 1, then that summation, this expression is approximately equal to a I naught into e to the power of V d by neta V t. Then if you are differentiating with respect to the a Vf, then that Rf, the forward resistance Rf is given by a neta V t divided by If, where that V t, if the temperature is constant, neta is 1 for silicon, then this is nothing but 26 millivolts divided by a forward current If, where what is If? If is the forward current, that is the unit of this forward current is nothing but a milliamperes. Therefore, milliamperes cancels, then Rf is to be a very small, that is about a some 10 volts, 10 ohms to 100 ohms, that depends on the region where you are taken. In the linear region, the diode resistance is very high, means moderately higher, and if you consider the in a saturation region, the diode resistance is small. And similarly, if you want to determine the reverse resistance, then once again you have to define, we know that already that that I d is IR is ID is equal to I naught into e to the power of Vd by neta Vt minus 1. When the diode is reverse biased, then that diode voltage up across the Vd is negative minus Vr. Then this exponential e to the power of minus Vr by neta Vt is much smaller than 1. Then ID is approximately equal to I naught. If you are differentiating this a reverse current, then that RR is approximately equal to infinity under the ideal condition. Using these parameters, that is a RF, RR, C diffusion capacitance CD, and a transition capacitance when the diode is reverse biased CT. Using these parameters, you have to determine the model the diode. Means in the diode modeling, you are using the diode can be replaced with its equivalent resistance in terms of RF, RR, CD and CT. At low frequency, diodes at low frequencies, then the diode can be modeled with, means that diode can be replaced with an ideal diode, its internal resistance and V gamma 0, and then this is denoted with resistance RF, and then this value a V gamma battery. When the diode is reverse biased, then the diode is replaced with simply an RR. Using these parameters, a nonlinear device can be modeled as a piecewise linear model. Then this is to be determined when with respect to the V gamma, if the input voltage, applied voltage is less than V gamma, then that voltage means current flowing through the circuit is 0. If the voltage exceeds that V gamma, diode is forward biased, and then its slope is approximately equal to 1 by Rf. When the diode is reverse biased until it is 0, that passing through, then that the resistance of the slope of this is to be 1 by Rr. Even the diode is modeled as an high frequency, means diode can be operated at high frequency. This combination can be, the diode is to be replaced with an RF and is followed with a parallel combination of CD. It is also known as a junction capacitance, because that CD is much greater than CT. When this diode is to be replaced, means at high frequencies, the diode can be replaced with its equivalent model RF by RF is in parallel with a diffusion capacitance CT. When the diode is reverse biased, the diode is replaced with RR, and then it's a transition capacitance CT. With this, we conclude that a diode can be modeled as a piecewise linear model, and diode is replaced with its equivalent resistance RF at low frequency and RR, and at high frequency it is a parallel combination of RF and a R and a capacitance CD. Next, let us consider transistors. Transistors are invented by the three people in 1947. By Barton, in 1947, the diode is invented by Bratton and Shockley. These are got Nobel Prize in 1956. The diode is nothing but ability to change from a conductor to the insulator, and it is also known as a transfer resistance. That diode transistor can be combining that back to back connection of a diode, or it is consisting of a P, that two N type material and one P type material, and it forms a NPN junction, and then that symbol of that transistor as shown in this figure. if you already studied in the earlier semester that a transistor consisting of the 3 terminals, one is collector, emitter and a base, where base is common for, there is a junction there. If you observe that transistor consisting of the 2 junctions, one is at the junction at emitter and a base, that is known as JEB, a emitter base junction, and a junction at a emitter and a base, collector and a base, it is denoted with a JCB. There are 2 junctions, therefore this transistor is also known as a bi-junction transistor, and then there are it consisting of the 2 type of charge carriers, therefore the transistor is also known as a bipolar device. The transistor can be configured by back-to-back connection of the 2 NPN diodes. It forms the 2 type of transistor, one is an NPN transistor, other one is an a PNP transistor, and then corresponding symbols are shown in figure. Now, if you consider that current flowing through that operation of a transistor, there are 2 junctions, a emitter based junction and a collector based junction. Do you think how many terminals are required for the input and the output? If you are observing this diagram, for any connection, there are 2 input terminals are required and 2 output terminals are required. But here means totally we required 4 terminals, 2 at input and 2 at the output. But a transistor consisting of only 3 terminals, hence you have to make one of the terminal is common for both input and the output. Based on this common, we can classify the transistors into a common base, a common collector and a common emitter and a common collector configuration. If you consider there are 2 junctions, already we specified it transfers changes the state from a conduction to the insulator, hence that a emitter based junction or input junction is always a forward biased and a collector based junction is always reverse biased for the proper amplification. When this emitter based junction is forward biased, if you are applying an voltage VBB, when that means that this junction is forward biased, then that whatever the charge carriers, means here in this is an NPN transistor, these electrons are crossing over that junction. When that electrons are crossing from emitted from an emitter, it is passing through a base. Then due to that these electrons are some of the electrons are recombined with a holes, and some of the electrons are means from the charge carrier from the p type material, that holes are moving in the opposite direction. Means because this base is lightly doped and then that width is very small, and most of the electrons are passing through that junction, it forms the collector current IC. This collector current IC is approximately equal to alpha times IE, where alpha is defined as the ratio of the collector charge carriers to the emitter charge carriers. This is with respect to the majority charge carriers. When this diode is reverse biased, means this junction is reverse biased, means these electrons are means whatever charge carriers are moving towards this junction, and then it forms a reverse saturation current. This reverse saturation current is to be denoted with ICBO. It is nothing but a reverse saturation current of a collector based junction. These are the some of the current are the flowing through that transistor. Now, let us consider a transistor current and voltages. If you consider the transistor, here you consider a common base configuration, that NPN transistor, that emitter base junction is forward biased and collector base junction is reverse biased. Due to that, if you consider this an voltage VBB, then voltage across, there is no resistances here, whatever the voltage appears across this, therefore it denoted with an VBE. If this voltage across this is to be VCC is applied, then that voltage across this junction is to be VCC. Because when the diode is forward biased, means base emitter junction is forward biased, then that current flowing through that is to be denoted with IE. Then this emitter current IE is exponentially increases, because when this junction is forward, it is acting as a simply diode. Means this we have to consider, and then this current is increases. and then voltage up across this is to be almost on V gamma only. It is equal to a VBE, a knee voltage of a diode. If we consider this junction, base collector junction is a reverse biased, and then whatever the voltage applied, that entire voltage appears across the junction, this is denoted with VC. When this, due to the forward biasing of this junction, then even if that input voltage VI is increases, that voltage up across the junction is V gamma is constant, and only that current IE increases. Because of this reason, this a transistor is to be also known as a current control device. Current control device. Now, do you think what is the resistance of this when the diode is a transistor is forward biased? When the transistor is forward biased, then this junction offers a very small resistance because it is acting as a conductor. This resistance is small. And when this junction, that in the other side, that collector base junction is reverse biased, it is acting as an insulator. Its resistance at this junction is a large, that is higher than that on input resistance. With respect to this transistor, that NPN transistor, various current flowing through this circuit as shown in this diagram, means that voltage between the junction, that current means between the collector and a base junction is VCB, and voltage between means this VCB is indicating means you have to measure the collector voltage with respect to base. Therefore, hence we have defined this symbol is positive and this is negative, and then this VCE is to be defined as a collector voltage measured with respect to the emitter, and VBE is measured with respect to the base voltage with respect to the emitter. And similarly, that current flowing through the circuit is given by IB is the input current, IC is the collector base collector current, and I is the emitter current. These two current are enter into the transistor and IE is leaving. Therefore, this IE is equal to IB plus IC. Then if you know the relation between the current and a voltage, then why we need to study these things? Because we know that already in a transistor configuration, the two terminals are required for the input and two terminals for a output for any system, but in a transistor we have only 3 terminals. Hence, we have to find, that means we have to make one of the transistor terminal is common for both input and the output. Hence, we can say that based on that we are to defining that CB is the common base configuration, CE is the common emitter configuration, CC is the common collector configuration. In this common base configuration, that input is applied between the base and a emitter, and output is taken across the collector and a base, and then current is, in case of a common base configuration, a input current is IE, voltage across this is denoted with VEB, because you have to measure the emitter voltage with respect to the base, and output current is IC, and the output voltage is given by VCB. And similarly for the emitter, common emitter, that input current is IB, voltage is VBE, and output current is IC, and voltage is VCE. And the common collector, what is the current flowing through that common collector, input and output? If you make a sense here, that common collector configuration, that input current is IB, and input voltage across this junction is nothing but we have to measure with respect to the base with respect to the collector, therefore it is voltage is VBC. And similarly for the output junction, output circuit, that output current is IE and output voltage is VEC. Here the second suffix is indicating that in either voltages, that indicates you have to measure with respect to what. If this junction is terminal is grounded, we have to measure only either VB or VE respectively. Then if you measure these parameters in a common base configuration, that we define these parameters, and then what are the parameters you are going to measure, means you have to define the current and voltage relations. If you are applying KVL to this entire loop, then you are going to get, if you are from this is plus to minus, we can say that this is minus VCB, plus to minus minus VBE, minus to plus, this is plus VCE equal to 0. Then that voltage and relationship between the among all the 3 terminals is given by VCE is equal to VCB plus VBE. This is the voltage relationship this is useful to modeling a transistor, one point. This can be obtained by using a Ebers mole model. Next, another point is, if that transmitter is parameters, if you are interchanging the notations, for example, I want to measure what is the relationship between VEB and VBE. Because these two voltages are measured between the same junction, base with respect to the emitter, first one, second one. This is, we have to measure emitter with respect to base. Hence, that relationship between that VEB and VBE is given by negative of that VBE. Similarly, this VCE is equal to minus of VCE, and this VCB is equal to minus of VBC. These are the voltage relationship between the NPN transistor, and then that relationship between the junction voltages. And similarly, that current flowing through, that is given by I is equal to IB plus IC in case of an NPN transistor. In PNP transistor, that direction of this current, emitter current, is opposite to that of an NPN current. Hence, this IE is given by minus of IB plus IC. These voltage and current relationships are helps to model a AC model of a transistor in the subsequent chapters. Next, if you consider these transistor parameters, then how to determine these parameters? Next, already from the diode we defined that parameters are, one is RD, nothing but RF, a forward resistance, and RR is the reverse resistance. But here, because we have to measure this from only on VI characteristics. In case of a transistor, there are two input terminals and output is to take other two terminals. Based on this, it depends on the configuration, you have to define that input and output characteristics of a transistor. These input and output characteristics are varies. That input and output character, this transistor parameter, why we have to study transistor characteristics? To understanding this transistor functioning, we need to understand that as transistor characteristics. Here this I am taken only on one example of a common emitter, a characteristics, because you are more frequently using these parameters, a transistor characteristics and a common emitter parameters in this transistor modeling of the first chapter. Hence, instead of considering that a common base and a collector configuration, we are consider a common emitter configuration. Before discussing the transistor characteristics, what is the relationship between the currents? Because already we know that I is equal to IB plus IC. Then what is the relationship between the common base, common collector, common emitter, a current relationship? We know that already in case of a common base configuration, that IC, output current IC is equal to alpha times IE. This is nothing but we have defined that alpha is nothing but a ratio of a majority charge carriers in the collector junction to the majority charge carriers in the emitter junction. Hence, we can define in terms of the transistor gain, this IC alpha is also known as IC by IE, where this is to be known as a current gain of a transistor in common base configuration. Similarly, we are to defining a common emitter gain in a common emitter configuration, that is to be denoted with beta. This is the ratio of a collector current to the base current IB, IC by IB. Then in case of a common collector configuration, that is to be given by gamma, this is equal to IE by IC, because that output IC by IB, where IE is the output current and IB is the base current. Then what is the relationship between alpha, beta, gamma? We know that alpha is given by IC by IB and beta is given by, alpha is given by IC by IE and beta is given by IC by IB and gamma is given by output current is IE and input current is IB. Then what is the relationship between alpha, beta, gamma? If you want to find the alpha, beta, gamma, you have to use and also we know that a emitter current IE is equal to IC plus IB. If you know this, if you are using this relation, we can find the alpha, beta, gamma. Means if you know that one of the parameter, we can determine the other parameters. This can be obtained by using this equation. If you take alpha in terms of beta, we know that this IE is equal to IC plus IB. Divide this on both the sides by IC, then this IE by IC is equal to IC by IE plus IB by I IC. Therefore, this I by IC is nothing but 1 by alpha. This is IC by alpha, this is equal to beta, this is nothing but 1 by beta. This is, if you take LCM, this is equal to 1 plus beta by beta. Hence, alpha is equal to beta divided by 1 plus beta. If I know this alpha is equal to beta plus 1 plus beta, if I know beta value, you can able to determine the current gain in the other parameters. If I want to determine this, manipulating this equation, then you are going to get a alpha beta in terms of alpha. This is nothing but alpha into 1 plus beta equal to beta. Hence, alpha plus alpha beta is equal to beta. Then alpha is equal to beta minus alpha beta. Hence, beta is equal to alpha divided by 1 minus alpha. Means, if I know that either alpha or beta or gamma, we can able to determine the other 3 parameters. These relations are used in the transistor modeling. If we once we know this voltage and current relationship, next is we have to determine the parameters. Whenever we want to model a transistor, we have to replace a transistor with its equivalent circuit. This is you are going to study in the next chapter. I want to modeling this transistor, we need to determine the transistor parameters. The transistor parameters are obtained from the input and output characteristics. Here we are shown this waveforms. One is an input characteristics, this is the output characteristics. That input characteristics are obtained already. We know that input characteristics are defined that in case of a common emitter configuration, that you have to consider this is your transistor, then the emitter is grounded. This can be defined as transistor RB, and then you are applying that voltage plus minus, and similarly there is a resistance RC, and then there is a voltage plus minus, this is denoted with VC. When you are applying these voltages, when this junction is forward biased and this junction is reverse biased, due to this forward bias, the current flowing through that circuit is IB, current flowing voltage drop across this is denoted with on VBE. And similarly, current flowing through this circuit is IC, voltage drop across this junction is PC. Means we have 2 currents and 2 voltages at the input and output respectively. For a input characteristics, you have to define, you have to find what is the independent parameter. Can you give me a solution? What is an input or a independent parameter? When you vary this voltage V, BB, then because of this forward biased, that base emitter junction is always almost constant. It is depends on this VB is depends on this transistor, because already we know that this VB is equal to 0.7 for silicon and 0.3 volts for germanium. Hence, this IB is independent parameter. Then we are to defining that VB in a input characteristics, VB is a function of some function of that a input parameter, that is a voltage IB, input current, and in this case that already from the previous discussions we know that collector current is depends on the base current. Hence, that VC is the independent parameter. Means when the VCC varies, then because of this junction is reverse biased, means base collector junction is reverse biased, as the current voltage applied, then the drop across the junction is proportional to the VCC, then VC is independent parameter. We can say that input characteristics are a function of IB and some function of IB and VC, and similarly output characteristics are, because the other parameters are, this IC is a dependent parameter, this IC is a dependent parameter, is another function of that IB comma VC. Means both a input characteristics and output characteristics are some functions of that input current and the output voltage. In general, we can say that for any configuration, that input voltage is a dependent parameter, it is a function of input current and output voltage, and output current is another function of a input voltage current and a output voltage. Using these parameters, means these equations you have to draw the function. If you vary this, these are the functions. Now, if you vary the input voltage, that base current varies. When you, because this also depends on that other parameter, input voltage not only depends on the applied voltage VBB, it is also depends on the collector emitter voltage. Means when you have to draw the input characteristics, you have to keep that VCE constant. Means you have to set this VCE constant for a 0 volts and then vary input voltage in terms of voltage, note down corresponding a base current and the VB. And similarly, you have to set another reading for VC is equal to some 1 volt and note down the base current and IB. You have to repeat this experiment. These characteristic curves are shown here. Means if you are consider this is a input a characteristics is a function of this current is to be a base current IB in terms of microamperes, this current is VBE is the base emitter voltage with a constant output characteristic curves. This is nothing but you can say that VCE 1 is equal to 0 volts and VCE2 is equal to 1 volt and VCE3 is equal to some 10 volts. Means is the VCE is increases, then that characteristics are moving shifted towards, means higher input characteristics. In the similarly from the output characteristics, we can say that you have to plot IC versus VCE, you are keeping that IB constant, then we can able to determine that VCE versus IC that characteristics. If from this characteristics we can classify into the 3 regions, one is an active region, cutoff region and saturation region. For applying these voltages, that if the input voltage is not sufficient, already this junction is forward reverse biased. When this junction is a forward bias, if the voltage is less, then there is no current is to be flowing through that junction, that current is to be this junction is known as a cutoff region. When the input voltage increases, this junction is forward biased and then this junction is still reverse biased, this junction is known as an active region. And the other region, if they are sufficiently, if you are increasing this voltage, then that current flowing through that circuit is almost constant, then this junction is from a reverse bias to the forward bias, thus that region is known as a saturation region. From these characteristic curves, always that for a faithful amplification or a distortionless amplification, that operating point is in the middle of the active region. From these we are going to measure the parameters. That parameters are nothing but you have to measure like RF, that input resistance Ri is to be defined as a change in the input voltage VBE by change in a input current IB with a constant VCE. Means you have to take the constant VCE, means you have to take for any one slope and then measure one thing. Second thing is from this as a ratio, it is a function of output voltage and output current, you are going to get a voltage gain, that is a ratio of change in a change in a output voltage with change in a input voltage with a constant IB. Means this can be obtained, you have to draw a line and then measure, take any 2 slope point and then you have to change, that will use the voltage gain. The other parameters measured from this output characteristics are a current gain, that is nothing but delta IC by delta IB with a constant VC. Means you draw one line and then parallel to the y axis, note and change the measure the current changes between the base current and the corresponding collector current ranges, that will give the current gain. And you have to measure the voltage, output voltage in the linear region with respect to the any one current. This is the region where you have to find the output impedance, output resistance R0 is equal to delta V C by delta I0 or IC. These parameters are used as transistor from the characteristics, you are going to measure these parameters. These parameters are used to model a transistor. There you have to define that Ri, R0, current gain AB and voltage gain AB and current gain AI. These parameters are useful for a transistor modeling. Now, finally, we have to summarize this class. We studied the diode characteristics and a transistor characteristics. In a diode characteristics, your diode is modeled as a low frequency model RF with V gamma, and at high frequency diode is to be replaced with RR, piecewise linear model. and at high frequency that diode is to be RF is in parallel with a junction capacitor, or simply say that a diffusion capacitance, and at the reverse bias this is to RR is replaced with a means RR is in parallel with a transition capacitance CT. This concept is used to model a transistor. Hence, these are the important parameters of the or a model of a diode. Please you have to go through this topic. And similarly, this from this transistor characteristics, you are going to measure these 4 parameters. Using these 4 parameters, you have to model. Means you are using the combination of the diode and a transistor parameters, you have to model a transistors at low frequency and high frequency. Thank you.